One issue that we run into whenever we're trying to calculate probabilities for normal distributions is that we have an infinite number of possibilities for the mean and standard deviation, and therefore we have an infinite number of normal curves. So if we were to try and find a probability for each normally distributed random variable, we would actually have to do a separate probability calculation for every normal distribution to find the area under the curve. So a solution to this is we essentially want to take everything to one normal curve that we already have the areas or the probabilities already figured out. So to do this, what we're going to do is we're going to standardize our normal curves using our standard scores from chapter 3. So essentially, remember this standard score, we also call this our z-score. And so basically what we're going to do is we're going to convert every normal distribution that we have to the standard normal distribution, or which we're also going to call the z-distribution. And then we actually have information on the areas or the probabilities for this curve. So the standard normal distribution, or the z-distribution, is just a normal distribution that has a mean of 0 and a standard deviation of 1. So because this is a normal distribution, the area underneath this entire curve is still going to be 1. It still continues on to negative infinity and infinity. But the difference is our mean is now 0, our standard deviation is 1. So basically what we're going to do is we're going to pick up any normal distribution that we already have with any mean and any standard deviation, and using our formula for the z-score or for the standard score, we're going to convert these normal distributions to this one. So think of it like picking up the ruler wherever it's at and sliding it down onto a standard ruler. That's what we're going to do. So to do that, we're going to use our formula for the z-score from chapter 3. So remember, the z-score or the standard score is just equal to the data value minus the mean divided by the standard deviation. So z is equal to x minus mu divided by sigma, or for a sample, it's equal to x minus x bar divided by s, depending on if you have population data or sample data. So basically what we've done at that point, so every single data value of the normally distributed random variable x transformed to a z-score, we're picking it up and we're taking that entire distribution down to the standard normal. So basically what our z-score formula does is it takes any normal distribution with some mean mu and some standard deviation sigma, and it converts it to a normal distribution with mean equaling 0 and standard deviation equaling 1. We then have tables that we'll talk about that we can use to find the cumulative area under the normal curve, or in other words, to find probabilities for this normal curve. So remember, area is synonymous with probabilities. So if we want to find a probability, we find the area using our standard normal curve table, which we'll talk about. So some features and properties of the standard normal distribution. So once you get out about negative 3.49, the cumulative area is essentially 0. It's close enough to 0. You can say anything out here is 0. So keep in mind, our normal distribution technically goes on and has space out there all the way down to negative infinity. But it's such a small amount of space, we can assume adding up all that space from negative infinity to negative 3.49 is 0. And then as we go up from there, our cumulative area is increasing, so we're adding more and more and more space, so the cumulative area is going up as our z-scores increase. As we get to z equaling 0, our cumulative area is 0.5, so we're halfway down the normal distribution, so we've covered half of the area. So our area at that point at our mean, so remember z equaling 0 is our mean, right? That's our middle. So the cumulative area at the middle is 0.5 because you've accounted for half of your data up to that point. And then as you get close to 3.49, again, you've just like with negative 3.49, there's very little data beyond that point now. And so you can assume that the area is pretty much 1. It's going to be like 0.99999 something. And so it's close enough to round to 1. You basically have all of your data accounted for by the time you get to 3.49.